the third lecture of Electronics Measurement and Instrumentation. I, Dr. Indu Prabha Singh, Professor, Department of Electronics and Communication Engineering, Shri Ram Swarup Memorial College of Engineering and Management. So, now in this lecture I will discuss about how this PMMC instrument is used as DC ammeter or voltmeter. In previous lecture I discussed about the what is the construction of permanent magnet, how this magnet is used as a voltmeter and ammeter, and then how this instrument is modified to act as a null detector, that is the galvanometer. So, in this lecture I will discuss the PMMC DC ammeter, multi-range PMMC ammeters, PMMC DC voltmeter and multi-range DC voltmeters, and then ohm meter. So, PMMC DC ammeter. So, PMMC DC ammeter, as we know that this in PMMC instrument there is a deflection torque produced due to the coil placed in a magnetic field, and that deflection torque is now controlled by the controlling torque of the spring. So, now this in PMMC instrument the deflection is proportional to the current flows in that meter. This PMMC instrument is very sensitive and this is used to measure very small amount of current. So, if we want to measure a large amount of current, so we have to place a resistance in parallel to that instrument, and the value of resistance which is placed at the parallel to that instrument, it should have very low value, so that most of the current will flow through this resistance and only a small current flows through this meter. Otherwise, the meter will burn due to I square R loss. So, and this meter the scale is calibrated, so that it shows the value of the current that this current I which we want to measure. So, if we see in this diagram, this Rm is basically showing the coil resistance, the resistance of the copper coil. So, this Rm is the coil resistance, this Rs is the shunt resistor resistance that we have placed, so that most of the current will flow through this resistance. So, here we can see that Vm is the voltage across this PMMC instrument. So, Vm is equal to Im into Rm. Okay, so, Rm is the moving coil resistance, Rs is the shunt resistance, Im is the full scale deflection current, Is is the current through the shunt resistance, and I is the total current which we want to measure. So, Vm is equal to here, Vm is equal to Im into Rm. So, Vm is equal to Im into Rm, and this resistance, shunt resistance is in parallel to that resistance Rm. So, the voltage drop across this resistance is also equivalent to the voltage drop across this resistance. So, here the current is Is, so it is Is into Rs. So, Vm is equal to Im Rm is equal to Is Rs. So, now from here we can find out that Is is equal to Im Rm by Rs. Now, this I current is equivalent to this shunt current plus the meter current. So, I is equal to Is plus Im. Okay, and this Im then, and here Im and Is, as we know Is from there, Im Rm by Rs. So, here we can substitute the value of Is. So, it will be Im is equal to 1 plus Rm by Rs. So, by solving this equation we have to find out the value of Rs. So, the value of Rs should be Rs is equal to Rm Im by I minus Im. I minus Im is basically the I minus Im is Is. So, it is Rm by Im by Is. So, okay, so there is one question that we have to calculate the value of shunt resistance required to convert 2 milliampere meter with internal resistance of 120 ohm into an ammeter of range 0 to 200 milliampere. It means we have to convert our meter which is measuring the maximum current of 2 milliampere, we have to convert it into a meter that can measure 200 milliampere. So, as we know from the previous slide that the value of RS is Im into Rm by I minus Im. So, here from the diagram we can see I is equal to 200 milliampere and Im is equal to 2 milliampere. So, only 2 milliampere current can flow through PMMC instrument. So, remaining current, that is 200 minus 2, 200 minus 2, that is 192 ampere current will flow through this resistance. So, we can find out the resistance, the value of this. So, by solving these two equation Im into, so we have to substitute the value of Im and Rm. So, Im is 2 into 10 to the power minus 3, the value of current is 2 milliampere. So, it is 2 into 10 to the power minus 3 into 120 ohm resistance, and this I minus Im is 200 minus 2 into 10 to the power minus 3. So, the value of resistance is 1.21 ohm. So, we can see from this question that the current, the resistance, the meter resistance is 120 ohm, but the shunt resistance that we are using here to increase the range is 1.21 ohm. So, it is very low with respect to this resistance. Now, the second question is that moving coil meter require a potential difference of 0.45 volt across the full scale deflection, that means Vm is 0.5 volt, and fixed resistance, shunt resistance, it is having 0.101 ohm, and the coil circuit resistance, that is the coil resistance Rm is 1 kilo ohm. So, we have to find out the value of shunt, this Rs, to make this meter, the full scale deflection, to make this meter that can measure 1 ampere current. So, we have to make this meter to measure 1 ampere current. So, again we know the Vm is 0.5 volt, and since both the resistance are parallel to each other, so the same voltage drop will appear across both the resistances. So, Im is equal to 1 kilo ohm, we can find out the value of Im because Vm is given, Rm is given. So, it is 0.5 volt by 1 kilo ohm and it is 0.5 milliampere. So, by this equation Is is equal to Im, Rm by Rs, we can find out the, when we substitute the value, we know that the shunt resistance value is given by Rm by Im divided by I minus Im. So, by substituting this value we have to find out the value of resistance, and we see the value of resistance is 0.5 ohm. So, when we are making this we are converting a PMMC instrument to measure 1 ampere, and instead of here we can see the value of Im is 0.5 milliampere. So, 0.52 we have to convert it into 1 ampere. So, the value of resistance Rm is 1 kilo ohm and here the value of resistance is 0.5 ohm. So, that is why we need very less resistance to increase the range of the ammeter. Similarly, one more question is there कि full scale deflection is 10 milliampere, internal resistance is 100 ohm, that is Rm is 100 ohm. What value of shunt resistance required to convert it to have full scale deflection of 1 meter? So, again we have to find out Vm. So, Vm is the voltage is this resistance into current. So, it is resistance value into current. So, it will be 1 volt. So, now we have to find out the shunt resistance. So, we know the current that will flow through the shunt resistance is the current, that is 10 ampere minus this current that is flowing to the PMMC instrument. So, 9.99 ampere current will flow through the shunt resistance. So, then we have to find out the shunt resistance value, that is the voltage divided by the current. So, its value is 0.1 ohm. So, in this way we can see that the shunt resistance which is placed to this PMMC instrument to increase the current range of the meter should be very low. Now, we can make a meter to measure different value of current, means there is a meter. So, there are so many scale. One scale is that is measuring by 0 to 10 milliampere. Next we need an scale that can measure 0 to 100 milliampere. So, we need one more scale, suppose it can measure 0 to 1 ampere. So, for this reason we have to make a meter that can measure many values of current. So, for this we need to place shunt resistance of multiple values. So, here this is a multi-range ammeter. We can use two type of resistance. The first is the multi-range ammeter using switched shunt. So, there are parallel resistance, series of parallel resistances, and this is the PMMC instrument. So, if we connect, if there is an pointer, there is an connecting switch. So, when this switch connects, suppose this is connect to first position, means this RS1 is in parallel to this PMMC instrument. So, this is the lowest value, means if RS1 is higher, because the voltage of this resistance is same as the voltage across this resistance. So, if the voltage is same, so if we want to measure higher value of current, we should keep the resistance low. So, here the low value of current is measured. So, the value of resistance is high. So, here RS1 is greater than RS2 is greater than RS3. So, when this pointer is at this position, the switch is at this position. So, there is current, the I current is, again it is divided into two parts, one I that is flowing here is Im, and here the current is IS1. Similarly, if we put the switch at this position, then what will happen? This RS2 resistance will be in parallel to this meter. So, by using this switch we can change the value of resistance, and in this way we can change the range of the current that we want to measure. So, RS is basically shunt resistance required, and the lowest value of RS is required for the highest range of I. So, now we can see this value of current by this example. So, here the question is 100 microampere full scale deflection meter is required to measure the current range of 1 meter, 1 milliampere, 10 milliampere, 100 milliampere and 1 meter. So, here we have to make this one more scale, that is 0 to 1 milliampere. So, this scale we want a single meter, in single meter we can measure all these values of current. So, for this we are using this shunt resistances. So, as we can see that Vm is equal to Im Rm. So, here is in this the full scale deflection current is given 100 microampere. So, 100 microampere and the resistance is 10 ohm. So, the voltage drop across this meter will be 100 microampere into 100 ohm resistance. So, it is 10 millivolt. Okay. So, same resistance drop will appear across all the resistances. So, suppose if this switch is at this position, means we want to measure the current that is between 0 to 1 milliampere. So, we will place this switch at this position, and now we have to find out the value of this resistance. So, value of this resistance will be again Rs is equal to Vm by divided by the current that is flowing through this meter. So, current here the current is 1 milliampere and this meter current is 100 microampere. So, that is 1 milliampere minus 100 microampere. So, it gives the value of 11.11 ohm. Similarly, we can calculate the second value, third and fourth. If you see in this calculation that the value of Rs is 0.01 ohm, the value of Rs3 is 100, this Rs is 0.1 ohm, then 1 ohm, then 11 ohm. It means when the range is increased, the value of resistance is decreased by 10 times. So, because the range is increased by 10 times. So, what we can say, this value of resistance and the accuracy of measurement, because this resistance have some plus minus values. So, the resistance value is very much changing, that is why this type of arrangement is not preferred, because there is so much difference in the value of resistances. So, the second type of multi-range PMMC instrument. So, here we use alternate shunt, that means the shunt is connected in series resistances. Okay, this resistance is placed in shunt of this PMMC instrument, but they are connected in series. So, what will happen if the switch is placed at first position? So, the current is flowing through PMMC instrument and the second current is flowing through all three resistances, means here the shunt resistance value will be R1 plus R2 plus R3 if it is placed at this position. So, it will be Rs is equal to R1 plus R2 plus R2 plus R3. Okay. So, this is Rs1 first shunt resistance when it is placed at first position, then it is R1 plus R2 plus R3, and when this switch is placed at second position it will be, now this is R1 plus R2. So, Rs2 will be R1 plus R2, but the current is flowing from here and then if it is placed at this position then it will flow through this position. So, the PMMC instrument, this Rm resistance is also connected with R3. So, the total resistance that is the PMMC instrument offer, that is Rm plus R3. Similarly, if it is placed at this position then R1 is in shunt resistance and Rm, R2, R3 are in series resistance. Here if we place this value, the low value is measured here and the high value is measured over here. So, this resistance, this combination is better because the value of resistances is not much varying. So, now voltmeter. So, as we know, when we want to measure voltmeter, so again this PMMC instrument can measure very small amount of voltage. So, we need a resistance across which the maximum voltage should be dropped. So, here we place a resistance Rs which is in series with this PMMC instrument, and the value of resistance Rs should be very high. So, that the maximum voltage drop appears across this resistance and only a small amount of voltage drop appears across PMMC instrument. So, if we can denote it by Vs, so if we denote it by Vs, so the total voltage V is equal to Vs plus Vm, and here Vs should be much greater than Vm. So, current is same, so Rs should be much greater than Rm. So, here if we see the Rs is the series multiplier resistance, V is the full scale DC voltage that can be measured by the instrument that we want to measure by the instrument, Im is the full scale deflection current and Rm is the internal resistance. So, if we apply KVL around this, then we find out V is equal to as I have written here, V is equal to Vs plus Vm. So, Vs is equal to Im Rs plus Im Rm, and if we take Im as a common, it is Rs plus Rm. So, the value of series resistance should be R is equal to V minus Im Rm divided by Im. So, it should be V by Im minus Rm. So, this value of resistance if we place in series with the PMMC instrument, then we can measure the higher value of voltage by this PMMC instrument. So, again multi-range voltmeter with switched multiplier resistor. So, again we use a parallel combination of resistances, and as we know in a voltmeter the resistance value should be very high. If value is high, then it will measure high voltage. So, here the value of R3, the resistance is very high. So, we can write Rs3 should be very high, Rs3 should be very high to the Rs2 and it should be greater than Rs1. Okay, so if the voltage higher value of voltage we want to measure, then we place this switch to the this position. Then if we want lowest value of the voltage to be measured, then we put the uh, switch at that position. So therefore, the multiple resistance are RS1, R2, and this will be, they are all are having special values, and that we can calculate by using the equation this. RS is equal to V by Im minus Rm. Now, second multi-range voltmeter, that is using series connected multiple resistor. So, here the resistor in previous type of multiplier resistor, the resistors are used in parallel to each other. Here the resistances are used in series with each other, and there is a switch. So, when switch is at this position, it means only the Rm and R1 is connected in series. So, if the value of R1 is whatever the value of R1, the voltage V is only the Im into Rm plus R1. So, if it is at, suppose it is a position A, so it is suppose the position 1, 2 and 3. So, if it is at position 1, so at position 1, what will happen, this V is equal to the voltage that we can measure is Im into Rm plus R1 only. Again, if we want to measure more voltage, then we have to put this switch at the second position, and at that time the voltage will be V2 will be Im Rm plus R1 plus R2. So, this is the value. Similarly, if it is at position 3, then it is Im is equal to V3 is equal to Im Rm plus R1 plus R2 plus R3. So, as we want to increase the range of voltage, we have to increase the resistances. Here the value, the difference between the value of resistances is very low, because they are connected in series, and in every calculation the resistances are added. So, loading effect, and if we are using a voltmeter that has a very low resistance, then when we connect it to a circuit to measure a voltage across any resistance, suppose here we want to measure the voltage across this resistance. So, what will happen if the resistance of voltmeter is very low? So, what will happen ki the total resistance of the circuit will reduce, and this meter will also draw the current. So, if the current that is drawing by the meter, that is IV, if IV is comparative to IR2 is not less, then there is a drop across meter. So, overall reading will change. So, we must have higher value of resistance of voltmeter. So, RV should be much greater than R2, and so IV should be much less than IR2. So, ideally we assume that a voltmeter has infinite input resistance, and so it should draw very low current. Then ohm meter. So, ohm meter is an instrument that is used to measure the resistance of any circuit. So, in ohm meter we need a supply voltage, because we are actually measuring the current, but this resistance, if V is constant, so V is equal to IR. So, V is equal to IR. So, if V is constant, so we can if I is increasing, R is decreasing. So, this is the there is a reverse relation between I and R. So, by measuring this R, I, we can measure the value of R. So, here we need a battery. So, VB battery is here. The unknown resistance, whose resistance we want to measure, is placed between 2 points, and then internal resistance of this meter is Rm, and R1 is the series resistance. So, standard known resistance is R1, Rx is the unknown resistance. So, from this circuit we can see the VB is equal to, if we apply KVL, VB is equal to the current Im into Rx plus R1 plus Rm. So, this Im is equal to Vb divided by these two. So, here the PMMC instrument resistance is very low. So, we can ignore this resistance and then we can calculate the value of Im is equal to Vb by Rx plus R1. Now, the scale of meter is like 0 ampere to suppose it is of 100 milliampere. So, the value of resistance scale should be opposite to this 0 ohm to here some value of resistance. So, for this we have to calibrate the this scale of the resistance. So, how do we calculate? So, first if we open this Rx and then we will see what is the meter detecting. So, the deflection of meter is at this point because the current is 0, there is no current. So, current is 0, it means ki resistance is maximum. So, the meter will show hereby some position. So, when Rx is infinite, Im is 0. So, meter is showing 0 current. So, maximum resistance. Then if we short these two terminals, then we read the meter reading. So, it will show the 0 resistance and because the current is full. So, it will places 0 resistance. Similarly, different values of taken. So, you can see the scale of the resistance here, the current meter reading is 0 microampere to 100 microampere and the resistance is opposite to that 0 ohm to infinite ohm. So, similarly, we can take if Im is equal to half full scale. So, that we have to find out the value of middle of this resistance. So, by this putting different values of Rs, we can find out the different values of the scale. So, we can place those values on the scale and by that we can measure the value of resistance. Now, again we need a 0 adjustment because without 0 adjustment we can't find the value of the current. So, for the 0 adjustment we are placing one resistance parallel to the meter and when we want to keep the meter 0, but it means when there is no current the meter will deflect at 0. So, the one R2 resistance is placed in the parallel to. So, when we vary this resistance to keep the meter reading 0, at that time this Rx is to be removed. So, the reading shown by the meter is correct, okay, when battery falls due to the time period. So, we can adjust the meter reading by varying this R2 resistance. So, thank you all. So, we have learned about the how to convert a PMMC instrument into an ammeter and voltmeter, then multi-range voltmeter and ammeter, and then the PMMC instrument to be converted into ohm meter. Thank you all.